Questions 21 through 25 on the 2013 Grade 7 Gauss Math Contest. In the addition shown, P and Q each represent a single digit, and the sum is 1 pp7. What is P plus Q? 7p, 6qp, qqp, and then the sum is 1 pp7. All right, so let's talk about this. So first, let's look at that column. We have 3p is equal to 7. Well, obviously, it's not going to be 7 because p is a digit. It's an integer. Well, what about 3p equal to 17? That would mean 7 and then carry the 1, right? Well, again, 17 doesn't divide 3. How about 3p equal to 27? Okay, that works because p now is 9. Okay, perfect. So let's get rid of all these p's and let's put in 9 since we have concluded that p is 9. So 9, 9, 9, and then 9 and 9. Okay, so here we go. Now we have to find q. So 7 plus q is equal to 9, correct? Well, not quite, because remember, 9 plus 9 plus 9 is 27, so we had to carry the 2. So don't forget to carry the 2. So now we can concentrate on this column. So that would basically be 2 plus 7, which is 9 plus 2q is equal to 9. All right, well, this could work if q is 0, right? Okay, let's see if q is 0, if that works. If q is 0, then if this becomes 0, then we get 7 plus 6, which is 13, and 13 is not 19. Okay, well, q is not 0 then. Okay, let's get rid of that. Q is not 0. Let me just write that in. Okay, what else can q be? Well, 9 plus 2q doesn't necessarily need to be 9. It could be 19, right? We could carry the 1, right? You put a 9 here, and then you put a 1 there. Okay, if that is the case, then what is q? Well, 2q would therefore be 10, and therefore q would be 5. All right, let's see if that works. This is 5. Let me just keep that in there. Let me get rid of those q's actually and put in the 5, since I'm pretty confident q is 5, but just to be sure, we'll check it all out. So now, does this work? Well, we have 2 plus 7, 9. 9 plus 5 and 5 is 10, so that's 19. So that 9 goes there. We carry the 1. Then if we add these guys, it's 8 plus 6, which is 14. 14 plus 5 is 19. So there we go. It all works out. So then it works when p is 9, q is 5, and they wanted p plus q. So that's just going to be 9 plus 5, which is 14. So number 21, the answer is C. An arithmetic sequence is a sequence in which each term after the first is obtained by adding a constant to the previous term. For example, 2, 4, 6, 8, and 1, 4, 7, 10 are arithmetic sequences. In the grid shown, the number in each row must form an arithmetic sequence, and the numbers in each column must form an arithmetic sequence. The value of x is. All right, it's grade 7. If it was grade 12, it'd be a piece of cake, but it's grade 7, and you have to be sympathetic to the fact that you probably haven't learned about arithmetic sequences yet. And that's why they gave you a couple of examples. So basically what it means is that you have a and then a plus d, a plus 2d, a plus 3d, like that. So for example, if a in this case is 10, then we'd have 10 plus d, then 10 plus 2d, then 10 plus 3d, like that. And they're telling me that everything is an arithmetic sequence in a row or in a column. Okay, so let's just concentrate on this row. Hopefully I'll be able to figure out these two values. All right, well, this guy is my first one, okay. This is 10 plus d, but I don't know what's d. But this is going to help me because this is right there. So that means that 10 plus 2d is 36. And therefore 2d is 26, and therefore d is 13. Okay, perfect. Now that I have d, I can figure out that and that. So this guy is 10 plus d, so d is 13, so that's 23. And this guy is 10 plus 3d, so that's what, 39 plus 10, so that's 49. All right, so let's put those in. This is 23, and this is 49. Okay, now we're going to do the exact same story, but on that column this time, these numbers. So here we go. Again, these are going to be of an arithmetic sequence. So it's going to be, say, A plus D, A plus 2D, A plus 3D, like that. And A, we don't know, we don't really care. We're just really interested in that X. So 25 is equal to A plus D, and 49 is equal to A plus 3D. So we got two equations, two variables we can solve. Subtract them, and we get 49 minus 25, which is 24. And here the A minus A cancels. 3D minus D is 2D. And therefore D is equal to 12. So if D is equal to 12, we can plug it back into this guy to get A. 25 is equal to A plus 12, and therefore A is 13. Perfect. We got D, we got A. Now we can figure out what is X, because X is equal to A plus 2D. So A plus 2D is our X. A is 13. Our D is 12. So this is 13 plus 24. And that is equal to 37. X is 37, and therefore number 22, the answer is A. In the right angle triangle PQR, PQ is equal to QR. The segments Q, S, T, U, and VW are perpendicular to PR, and the segments ST and UV are perpendicular to QR, as shown. What fraction of PQR is shaded? Let's just give some numbers. It helps us. Let's just say that side is 1. And since PQ is equal to QR, QR will be 1. All right? So very first and foremost, the full big triangle PQR will have an area. I'll just write area here of 1/2 base times height. The base is 1, the height is 1, so that's a half. All right? So now we're going to keep doing this for a whole bunch of triangles. So the next one is when we've chopped the big one in half, and we've done that essentially by drawing a perpendicular QS, because they told me that QS is perpendicular to PR. When you draw that line, it chops it into half, so this becomes half of the big one. So that triangle is QSR, right? This one. And that's basically going to have an area that's half of PQR, which is that big one. So if PQR had an area of a half, QSR will have an area of a quarter. Okay? So there's no tricks here. It's just basically chopping it in half a whole bunch of times, as you will see. We do the same thing now with this guy. ST is perpendicular to QR, right? They even tell you that. So that means ST chops that triangle into half. So STR, that triangle, STR will be half of that triangle, which was QSR. So if QSR was a quarter, STR will be an eighth. All right. Again, do the exact same thing. Now we're going to look at that one. STU. Say STU is a half of STR, because again, TU is perpendicular to SR. And they told me that right here. TU is perpendicular to SR and also PR, right? It's the same line. So STU is a half of STR, so that means STU is a 16th. And now let's see here. We have to understand that STU was the same as UTR, right? It's just the other half. And then now I'm going to concentrate on this guy, UVR. UVR, that triangle will be a half of the previous one. So that'll be 1/32. And then finally, we get to that smallest guy, UVW, and that's going to be a half of the previous guy, so that'll be 1/64. So basically all we did was we kept chopping triangles into halves and coming up with their respective areas. Now, what fraction of the PQR, the big one, is the shaded region? Okay, so the shaded region is STU plus UVW. And then we have to calculate the fraction over the big one, PQR. Okay, STU is 1 over 16. UVW is 1 over 64. And then PQR was here, half. So this is what I have to solve. Multiply top and bottom by 4, so I get 4 plus 1 over 64. Invert and multiply, and I get 2 over 1. And this will be 5 times 2, which is 10 over 64. In lowest terms, 5 over 32. Number 23 is 5 over 32, and that would be choice D. One face of a cube contains a circle as shown. This cube rolls without sliding on a 4x4 checkerboard. The cube always begins a path on the bottom left square in the position shown and completes the path on the top right square. During each move, an edge of the cube remains in contact with the board. Each move of the cube is either right or up. For each path, a face of the cube contacts 7 different squares on the checkered board, including the bottom left and the top right squares. The number of different paths that will not be contacted by the face with the circle on any path is. Let's explain this question first. Basically, this cube right here is rolling. It's basically going to go, let's say here, and then here, and then here, and then here, here, here. And there's several paths, right? That's one path. Another path is that it could go here, then here, then here, then here, then here, then here, like that, right? The rule is that it can only go right or up. So it can either go right or it can go up. It can go up, it can go right. But it cannot go left and it cannot go back down. And that's what they mean by that it contacts 7 different squares. In any such path, it's only going to hit 7 times. So for example, 1, 2, 3, 4, 5, 6. And then don't forget the first one, right? That's going to be 7. Let's do it again. We have the first one, 2, 3, 4, 5, 6, 7. So what they're saying is focus on that circle. They want that circle to touch the board. So how do I do that? Well, let's flip this down. If I flip that down, the circle is still going to be in this orientation, correct? But then if I flip it this way, the circle will now be on top, and it takes a little bit of 3D visualization. If I flip it again, the circle will now be here. It'll be sort of on the other side. And then finally, if I flip it again, then it will be touching the board. So that is basically the crucial element of this question, is the 3D visualization. Now, some of these are pretty straightforward, so I'll do the straightforward ones, and then I'll explain how to do the rest. I'm just going to do these ones first. It's going here, then it's going here, then it's going here. Notice when that happens, the orientation of the circle will always be facing the same way. If you flip this here, and then again you flip it here, and then you flip it here, the circle is always going to be facing me. So that means those squares will never have that circle touching them. So if I were to make a little grid, right? Say this is my sort of grid, and I'll just break this up into 4x4 like this. This is my 4x4 grid. And the initial place that the cube begins is here, right? And that's represented here. That obviously is a no, meaning the circle does not touch the board. But then I've also hopefully explained to you that because it would never be able to touch those 3, these are also no's. This is a no, this is a no, and this is a no, right? Because, and I don't want to beat that to death, but I'm sure you understand it. Now we have to figure out which one of these guys is a no and a yes, and then we have to, in the end, count up all the no's. All right, so some of you can do that, or if you're practicing, just get a Rubik's Cube, tape on a little circle, and then figure out how you can do this. Or there's a cool little way, and this is that little table, that if we were to label these squares, this is say 1, 2, 3, 4, 5, 6, and so on. This very nice table shows all the squares that the circle will indeed eventually touch this checkerboard. And they're showing you how. So for example, the first yes that they have is for 7. So that means that yes, that square with the circle on it will eventually have a orientation where the circle touches the board. And they show you how. URR. Well, what is URR? U, it means up, and R means right. There's only 2 moves, right? Right or up. So let's talk about that first one. We started here, then you go up, so we go to here, then we go right, and then we go right. Okay, so that's how we get to 7. But then now, where's the position of the circle? These letters, T is top, R is the right face of the cube, O is on the board, and then is there any other? Oh, B is bottom, and I think those are the only letters that they have. Actually, they have a F, which is front. Okay, so now let's talk about the first one. When you go from this position to this position, so that you're going to end up here, that means that cube basically went down like that. So now the orientation of the circle is on top, and that's why it says T. Then you're going right, so that means now you're going here. When you do that, the cube, if the circle was here, now the circle will be here. So that means the circle will be on the right, and that's why it says R here. And then once the circle is here and you flip it once more, it will land on top of the board, and that's why it says O, which means on board. So I'm not going to go through every single one of these because you don't want to hear me go through that. That's going to be way too boring. But if you follow each of these, you'll see that all of them end up O, 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 like that. So all of these end up on the board. And because all of them end up on the board, it's a yes for all of those. So let's see, 7, 8, 11, 12. And then all of these guys are yeses. Yes, 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 yes. So that means these ones I had hopefully explained pretty well why it's a no. But that also means that these guys are no's. They're never going to be in an orientation where the circle is on the board. So now we have to count up how many no's we have. That's what that last sentence means. And the number of no's, 1, 2, 3, 4, 5, 6, 7, 8. So 8 is the answer to number 24, which is choice C. And like I said, if you got a Rubik's Cube, slap on a circle, make it look like that, and then start flipping it and go through this table, and you'll get, I'm confident, a very good understanding of this question, if you haven't already done so. A box contains a total of 400 tickets that come in 5 colors: blue, green, red, yellow, and orange. The ratio of blue to green to red tickets is 1 to 2 to 4. So I'll call it X to 2X to 4X. The ratio of green to yellow to orange is 1 to 3 to 6. So the ratio of green to yellow to orange is 1 to 3 to 6. So I will write Z, 3Z, 6Z. What is the smallest number of tickets that must be drawn to ensure that at least 50 tickets of one color have been selected? All right. So the first thing we have to do is find out the distribution of these tickets, considering that they all add up to 400. Well, Z represents the number of green tickets, but so does 2x. So that means that 2x is equal to Z. If 2x is equal to Z, that means x is equal to Z over 2. So put that here. 4x would be equal to 2Z. So put that here. And then 3Z would be equal to 6x. So put that here. And 6Z will be equivalent of 12x. So put that here. So I can add all these guys up. And if I do, that will equal 400. So x plus 2x plus 4x plus 6x plus 12x is equal to 400. So what does that give me? 3, 7, 13, and 25. So 25x is equal to 400. So that means x is 16. So plug those numbers back into here. So that means we've got 16 for blue. We've got 32 for green. 4x is 64. 6x is 96, and 12x is 192. So that's the number of tickets of each color. Now our task is the final sentence. What is the smallest number of tickets that must be drawn to ensure that at least 50 tickets of one color have been selected? Notice the spelling of the word color. Now you can tell it's a Canadian math contest. All right, so let's use extreme case scenarios here. We want to use the smallest number of tickets. Now, some of you might say, well, just choose 50 tickets. That's the smallest number, and it's the smallest of the answer choices. But here's the thing. If I choose 50, it doesn't ensure that I get 50 of the same color. Let's say I chose 50, but it was a few of them were green, and a few of them were red, and a few of them were yellow. That doesn't ensure. I have to guarantee. Now, how do I do that? And this is the way you do it. First, what you do is you select all of the blues. So that's 16 of them. So we've exhausted the blues. Now we select all of the green. That's 32. We're done. We've taken all the greens out. Right? Now we can't choose them, meaning we can't look and see that we're choosing them. But what I'm saying is this is the extreme case scenario that just by chance, when you selected 16, all of them happened to be blue. Then you selected another 32, and all of them happen to be green. It's an extreme case scenario. Now what we do is we say, okay, I'm not guaranteed of having the same color. I'm going to select 49 now of the red. And just by some chance, they all happen to be red. Then I'm going to select another 49 tickets, and by chance, they're all going to be yellow. And then I'm going to select another 49, and by chance, they're all going to be orange. The reason I'm doing it like this is because I have to guarantee that when I choose a certain number of tickets, that there's going to be 50 of the same color. This scenario does not produce 50 of the same color. You see what I mean? So this scenario is possible. And we have to look at any extreme case scenario where it's possible to not have 50. This is a possible scenario where I chose 16 blue, I chose 32 green, 49 were red, 49 were yellow, and 49 were orange. So let's add these up, and when you do, you get 195. So far, in this extreme case scenario, we don't have 50 of any one color, but the very next ticket that's chosen will push me to 50. It won't be a blue or a green because those are exhausted. Those have already been all selected. But the very next ticket I choose must end up being either a red, yellow, or orange because there still are some of those left, right? Because 64, 96, and 192 are the total, and I only chose 49 of each of them. So the very next one, let's say if it's an R, a red ticket, boom, I've got 50 of them. If the very next one happened to be a yellow, I've got 50 of yellow. If the very next ticket happened to be an orange, I've got 50 oranges. Oh, 50 orange tickets. So 195 plus the very next ticket, and that would be 196. So it's a good little challenge in terms of counting. And therefore, number 25, the answer is D.